some important terms used to describe magnetic properties of materials. Magnetic properties of materials. Used to describe magnetic properties of materials. Now, first one is magnetizing field. The magnetic field that exists in vacuum and induces magnetism is called magnetizing field. Such a magnetic field which exists in vacuum also and which induces magnetism in something else, which induces magnetism in a magnetic material like iron, steel, cobalt, and nickel. Such a magnetic field is called magnetizing field. For example, a toroidal solenoid having n turns per unit length. The magnetic field, set up in the solenoid is given by B naught is equal to mu naught Ni. This field is called magnetizing field caused by the so-called free current in the solenoid. So, the magnetizing field is that field which induces magnetism in a magnetic material. That is called magnetizing field. Now, second term is magnetic induction. First is magnetizing field. Magnetizing field. First is magnetizing field and second is magnetic induction. Magnetic induction. Magnetic induction. Now, what is this procedure? The total magnetic field inside a magnetic material, the total magnetic field is the sum of the external magnetizing field and the additional magnetic field produced due to magnetization of the material. So, any magnetic material has two types of fields. First, has two types of magnetic field. First is the magnetic field. First is external magnetic field, external magnetizing field. Magnetizing field is that field which induces magnetism in any magnetic material. So, magnetic induction is the sum of that external magnetizing field and the field which gets developed into that magnetic material because of its own property. So, that is called the sum of both these fields is called magnetic induction. Look, the total magnetic field inside a magnetic material is the sum of the external magnetizing field and the additional magnetic field produced due to magnetization of the material and is called magnetic induction B vector. This is called magnetic induction B vector. It is also defined as the total number of magnetic lines of force crossing per unit area normally through a material. Its SI unit is Tesla or Weber per meter square. So magnetic induction is B vector, its SI unit is Tesla or WB, Weber m to the power minus 2, Weber per meter square. Okay. Now third is magnetizing field intensity. Third is magnetizing field intensity. The ability of magnetizing field to magnetize a material medium is expressed by a vector H vector called magnetizing field intensity. Magnetizing field is such field. Magnetizing field is that field which produces magnetism in a magnetic material. That is called magnetizing field. And magnetizing field, how much strong is that magnetizing field? What is the ability of that magnetizing field to magnetize a material? That is called magnetizing field intensity and it is represented by H vector. Okay, its magnitude may be defined as the number of ampere turns flowing around the unit length of the solenoid required to produce the given magnetizing field. So H is equal to Ni, H is equal to Ni, and we know that B naught is equal to mu naught Ni. This is the magnetic field. This is the magnetic field which is developed inside a solenoid. So, the magnetic field of a solenoid is given as B naught is equal to mu naught Ni. Now, what is this Ni? In place of Ni, we can write now H. So, B naught is equal to mu naught into H. B naught is equal to mu naught into H. Now, H is B naught upon mu naught. B naught upon mu naught. Okay, is this clear till now?
Yes.
Its SI unit is ampere per meter. Ampere, ampere per meter is its SI unit. Now, fourth is intensity of magnetization. Now, let's understand all these terms. First is magnetizing field. Magnetizing field is that field which magnetizing field is that field which induces magnetism in a magnetic material. So such a field is called magnetizing field. Now, what is magnetic induction? Magnetic induction is the sum of external magnetizing field plus the magnetic field which is induced, external magnetizing field, the magnetic field which is produced inside the magnetic material due to magnetization. So the sum of both those fields is called magnetic induction, and that magnetic induction is called B vector. So and SI unit of B vector is Tesla or Weber per meter square. Now, third is magnetizing field intensity. How much strong is that magnetizing field? The capacity or the ability of the magnetizing field to magnetize a material is called magnetizing field intensity. Magnetizing field intensity is given by H. H is equal to Ni. Now, we know that for a solenoid, we know that B naught is equal to mu naught into Ni. In place of Ni, I can write H here. So H is equal to, and what is H? H is magnetizing field intensity. So H is B naught upon mu naught. Now, the fourth term is intensity of magnetization. Fourth is intensity of magnetization. Intensity of magnetization. The magnetic moment developed per unit volume. The magnetic moment developed per unit volume of a material when placed in a magnetizing field is called intensity of magnetization, or simply magnetization. When we place a magnetic material, for example, when we place a piece of iron inside a magnetic field, so the magnetic moment which is developed inside that piece of iron per unit volume is called intensity of magnetization. I repeat it, the magnetic moment developed per unit volume of a material when placed in a magnetizing field is called intensity of magnetization, and intensity of magnetization is given by capital M vector. So capital M vector is equal to small m vector upon V. V is volume. So magnetic moment per unit volume. Now, capital M is equal to what is this magnetic moment? Magnetic moment is either charge into distance between them. So Q into 2L upon what is volume? Volume is cross sectional area of a magnet into 2L. Okay. So if we wish to calculate the volume, of a magnet, then volume of that magnet is like this. And Anusha, this area is called area of cross section. So this is small a, and the length of the magnet is 2L. Length of the magnet is 2L. So small a, it comes with the help of this length into breadth. Length multiplied by breadth. And what is this? This one is height. So if I multiply length into breadth into height, so length into breadth into height becomes volume. Okay. So volume, in place of volume, I have written area of cross section into height. Height is 2L here. Okay, is this clear to you? Is this clear?
Yes, sir.
Okay. So from here we can cancel 2L by this 2L. So intensity of magnetization is Q upon A, means charge per unit area of cross section. Now on page number 26, please come. Let's see the next term. Next term is magnetic permeability. Now, what is magnetic permeability? Wait. Wait for a moment, please. The fifth term is magnetic permeability. What is magnetic permeability? The magnetic permeability of a material may be defined. The magnetic permeability of a material may be defined as the ratio of its magnetic induction B to the magnetic intensity H. So the ratio of magnetic induction to magnetic intensity, magnetic induction is B and magnetic intensity is H. So the ratio of B and H, the ratio of B and H is called magnetic permeability. So mu is equal to B upon H. This is magnetic permeability. Mu is equal to B upon H. SI unit is Tesla meter per ampere. SI unit of mu is Tesla meter per ampere. Now, sixth term is relative permeability. Relative permeability. It is defined as the ratio of the permeability of the medium to the permeability of free space. So mu r is equal to relative permeability of a medium upon permeability of free space. Mu r is equal to mu upon mu naught. This is called relative permeability. Okay, so till now we have studied 6 terms. So let's have a brief review of these 6 terms. After that, I have 2 more terms also. First one is magnetizing field. Magnetizing field is that field which induces or produces magnetism in a magnetic material. Magnetic material is iron, steel, cobalt, and nickel, which have some magnetic properties. Okay, so magnetizing field is that field which produces magnetism in a magnetic material when placed in that medium. Second is magnetic induction. Magnetic induction is the sum of magnetizing field plus the field which gets produced in a magnetic material. So the sum of both those magnetic fields is called magnetic induction B vector. Third is magnetizing field intensity. Magnetizing field intensity is the ability or capacity of this magnetizing field to induce magnetism in a magnetic material. This is called magnetizing field intensity. This is given by H. H is equal to N into I. Now we know that for a solenoid, the magnetic field inside a solenoid is given as B naught is equal to mu naught Ni. Now this Ni is equal to what? Ni is H. So we can write B naught is equal to mu naught into H. So H will be written as B naught upon mu naught. This is magnetizing field intensity. Magnetizing field intensity is H. It is H. Magnetic induction is B vector. Okay, now intensity of magnetization. What is intensity of magnetization? The magnetic moment developed per unit volume in a magnetic material is called intensity of magnetization. It is represented by capital M vector. Capital M vector is magnetic moment upon volume. Magnetic moment is Q into 2L, either charge into either charge. Here the charge, magnetic charge is Q, here is Q, so either charge into distance between them. So Q into 2L upon what is volume? Volume is area of cross section multiplied by length or height. So this is A into 2L. 2L will get cancelled out by this 2L and M will come out. Intensity of magnetization will come out to be Q upon A. Fifth term is magnetic permeability. Magnetic induction divided by magnetizing field intensity is called magnetic permeability. This is defined as mu is equal to B upon H. Now relative permeability. Relative permeability is mu r is equal to mu upon mu naught. Mu upon mu naught. So this is permeability of a medium upon permeability of free space. So all these 6 terms are clear to you? All the terms are clear or not? Okay. Okay. Now let's move on to the next term, magnetic susceptibility. Magnetic susceptibility. It is defined as the ratio of the intensity of magnetization, capital M, to the magnetizing field intensity H. It is denoted by chi M. This is known as chi, 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 chi. So magnetic susceptibility is chi M. It is defined by M upon H. Now relation between this is called magnetic susceptibility. Okay. Now the eighth term is actually eighth is not a term, it is a relation. Relation between magnetic permeability and magnetic susceptibility. What is magnetic permeability? It is mu. What is magnetic susceptibility? It is chi m. So we have to just establish a relationship between mu and chi m. Okay. Relation between magnetic permeability and magnetic susceptibility. If a linear magnetic material subjected to the action of a magnetizing field intensity H develops magnetization M, capital M, and magnetic induction B, then we know that B is equal to mu naught. B is equal to mu naught into H. B naught is equal to mu naught into H. And if we talk about B, B means magnetic induction. So magnetic induction is the sum of both external magnetizing field plus the magnetization which is being developed in the body. So it is the sum of both. That's why we have written mu naught multiplied by H plus M. H plus M. Now, but B is equal to mu into H. If we write here mu into H, in place of B, if we write mu into H, is equal to mu naught into H plus M. Mu naught into H plus M. Mu H is equal to mu naught. If we take out H common, then it will become 1 plus M upon H. H will get cancelled out by this H. So mu is equal to mu naught into 1 plus, what is this M upon H? M upon H is chi M. Chi M. Okay. And mu upon mu naught, if we take out this mu upon mu naught, it will be like this 1 plus chi M. So mu upon mu naught is mu R, a relative permeability. Mu R is equal to 1 plus chi M. Now tell me, is that clear to you?
Yes, sir.
Okay. Okay. Now the last topic of this chapter is left, hysteresis. Let's start with that one. Please wait for 1 minute. I am coming back. Okay. Now let's do this one, hysteresis. So next topic is hysteresis. Hysteresis. Anusha, there are three types of materials. There are three types of magnetic materials. One is diamagnetic, one is paramagnetic, and one is ferromagnetic. I will send you a sheet. I will send you a sheet in which there is a comparison of these three materials also. So that is a theoretical topic. Sometimes it can be asked in the examination. So there is one type of material called ferromagnetic material. Ferromagnetic material is that type of material in which we can magnetize it as well as we can demagnetize it. Are you getting it? If I take a hard piece of iron, and if I tie it with a magnet, then and place it for some time, like 2 months or 3 months, and after that, if I try to remove it from that magnetic piece, then that hard iron piece will get magnetized means it will also become a magnet. But if I want to remove its magnetism, if I want to demagnetize it, then it is not possible. So there are some materials, those materials are called ferromagnetic materials. Ferromagnetic materials can be magnetized as well as they can be demagnetized. So hysteresis in this topic, when a ferromagnetic sample is placed in a magnetizing field, means if we place a ferromagnetic material in a magnetizing field, means we want to magnetize it. The sample gets magnetized by induction. This sample gets magnetized by induction. Now, I will draw a graph of hysteresis. It will make the graph is very much important. Actually, we have to study this graph only in this topic, hysteresis topic. We have to study this graph only. So, what is this graph? What this graph says all about? Now, on x-axis we are taking this intensity of magnetization H, and on y-axis we are taking this one B. B is magnetic induction. So, first of all, uh, I am reading out from this theory. Anusha, are you listening? Are you there?
Yes, I am.
Okay, 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 okay. 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 So point O represents the initial unmagnetized state of a ferromagnetic sample. As the magnetizing field intensity H increases, the magnetic induction B first gradually increases and then attains a constant value. In other words, the magnetic induction B saturates at a certain value of H max. Saturates at a certain value of H max. So this is origin. This is origin, and when we magnetize it, then it becomes saturated at this point. So this is plus H max plus H max. Now this is point A, and this point we are marking here saturation. Saturation means at this point the magnetic field becomes constant, becomes saturated. Now, if the magnetizing field intensity H is gradually decreased to zero, now if we slowly decrease this magnetizing field to zero, then what will be observed? B decreases. B means magnetic induction. B decreases, but along a new path AB. Along a new path AB, it is found that the magnetic induction B does not become zero even when the magnetizing field H is zero. That is, the sample is not demagnetized even when the magnetizing field has been removed. Even when the magnetizing field has been removed. So we will do it like this. Hmm. So this point is B, this one is C, this point is B, this one is C, and this point is D. Now, if the magnetizing field intensity H is gradually decreased to zero, B decreases, but along a new path AB, it is found that the magnetic induction B does not become zero even when the magnetizing field H is zero. That is, the sample is not demagnetized even when the magnetizing field has been removed. So, what we are observing initially at point O is origin. Initially at point O, both H and B. Initially at point O, both H and B are zero. Both H and B are zero. It means that both H and B are zero. It means that there is no magnetizing field, so there is no magnetic induction. When we increase H slowly, when we increase, then this magnetic induction, it also increases, and it becomes constant. It becomes constant at a point A. Now, if we are demagnetizing it, demagnetizing means if we are reducing the value of H, if we are reducing the value of magnetizing field H, then the magnetic induction also reduces, but along a new path AB. So what we have observed, that H has become zero, but B has not become zero. So the value, this one OB, this value is called retentivity or remanence. On to page number 28 of your notes, it is written that the magnetic induction OB left behind in the sample after the magnetizing field has been removed is called residual magnetism or retentivity or remanence. So this one is called OB. OB is called retentivity. Retentivity means after removing, retentivity means after removing H, when H has become zero, magnetic induction has not become zero. It will remain. This is called residual magnetism or retentivity or remanence. Is that clear to you?
Yes, sir.
Okay. Now, now, next point, to reduce the magnetism to zero, the field H is gradually increased in the reverse direction. The induction B decreases and becomes zero at a value of H is equal to OC. At a value of H is equal to OC. So when at a value of H is equal to OC, so at this value of H, magnetic induction has become zero, and we call the value of reverse magnetizing field intensity H required for the residual magnetism of a sample to become zero is called coercivity of the sample. This one is called OC, is called coercivity of the sample. Coercivity of the coercivity of the sample. On further increasing H in the reverse direction to a value of minus H max, we reach the saturation point D located symmetrically to point A. Located symmetrically. It is symmetric to point A. Symmetrically to point A. Now, if H is increased in the forward direction, okay, look, what is this? This is minus H max. minus H max, and it is called saturation. Here it is called saturation. Okay, negative saturation. Now if we increase H again, what we will observe? Now if H is increased in the forward direction gradually means slowly, the point A is reached after going through the path DEFA, like this. So D E F A, DEFA. The closed curve ABCDEFA, first of all, we have increased H, the magnetic induction also increases like this. Now we are decreasing H, the magnetic induction is also decreasing like this. Now if we increase again, if we increase it again, then it is increasing till point A like this. So the closed curve ABCDEFA, closed curve ABCDEFA, closed curve ABCDEFA, which represents a cycle of magnetization of a ferromagnetic sample, is called its hysteresis loop. Is called its hysteresis loop. The phenomena of the lagging of magnetic induction behind the magnetizing field is called hysteresis. This phenomena is called hysteresis. Okay. Now, significance of the area of hysteresis loop. What is the use of this area? What is the use of the area of the hysteresis loop? So significance of the area of hysteresis loop. The area within the BH loop, the area within the BH loop is this, B and H. BH loop represents energy dissipated per unit volume in the material when it is carried through a cycle of magnetization. When a material goes through a cycle of magnetization, then how much energy is required, how much energy is dissipated in that, the area gives that energy dissipation. This one. This area gives energy dissipated. Energy dissipated in a cycle of magnetization. Is that clear to you?
Yes, sir.
Okay, Anusha, then this chapter is over. Moving charges and magnetism is also over, and this magnetism and matter is also over. Now, one more chapter which is coming in your exam is electromagnetic induction. So, shall we start with that?
Yes, sir.
Okay, wait.